Okay, we are going to start section 10.2 here today. One thing I just want to emphasize here is anytime a problem asks you to describe a distribution, what they're really asking you to do is they're wanting you to describe these elements that are in our acronym for CUS, which is to describe the center, spread, shape. Of course, the U is unusual values. That is a little tricky to do with these particular problems in this section unless you're either given a graph where you can tell that there would possibly be an outlier, or if you're given all the data values. So when you're asked to describe a distribution, you want to make sure that you are describing the center, the spread, and the shape, which can all be summed up then using this notation here. Okay, I know that we've just coming off the heels here of section 10.1, which is looking at the center is the difference between two sample proportions, the spread given by this formula on the formula sheet here, but you have to show the 10% condition first, and then the shape, you can say that it's normal provided for each population you have shown that the number of expected successes and the number of expected failures are all at least 10. Okay, and then you can summarize shape, center, and spread. Okay, so on the opening page here to this, we're going to start with something that we're familiar with from an earlier chapter, which is when we were describing just a sampling distribution for X bar. We're just talking about one single population. We would draw out a sample size N. We would calculate the mean of that sample. The shape of that is normal if we can say one of these three things. And I listed them in the order of easiest to most difficult. If the population is normal, if the sample size is greater than or equal to 30, that's our central limit theorem. Or worst case scenario, if we're drawing a graph, usually we do a box plot of the sample data. If there's no extreme outliers or extreme skewness, we can then go ahead and conclude that the shape is normal. It has to be one of these three things that we mentioned for us to say that it's normal. The center should be right in line with what the true mu value is, and the spread is this formula here on the formula sheet, provided we've done the 10% condition. Okay, of course, the other condition that needs to be mentioned is just that either the sample was taken randomly, or if it's an experiment, that the treatments were assigned randomly. What we're going to be focusing on, though, in this section is we're going to be focusing on, instead of just drawing out a sample from one population, we're going to be drawing out a sample from two populations, okay? And we're going to be doing the difference between those two samples. So that's going to create a sampling distribution for the difference of two sample means. What you'll notice here is our description is still basically the same, okay? Our shape, we can say it's normal if both populations were told to us that they were both normal, or if both the sample sizes are greater than or equal to 30, or if we made two graphs, one for each of the two samples, and both of those graphs reveal no extreme skewness or outliers, then we could conclude that the shape is normal. Okay, and we also have to make sure that we are acknowledging that both of the samples were taken randomly, or if it's an experiment, that both of the treatments for each of these were assigned randomly. Okay, we know the center is just the difference between the two means, and then the spread, which again is given by this formula on the formula sheet. Okay, that's the 10% condition, has to be shown for both populations. So we have to do that for each of the two samples. Okay, and then finally, this is going to kind of feel like an added condition here. We had this when we dealt with proportions as well. Since we are drawing two samples, one from each of two separate populations, we need to make sure that the samples are drawn in such a way that they are independent of each other. Okay, so these conditions that you see listed here, all four of those are listed very abbreviated here on this next page. Okay, and oftentimes we kind of link together and say in the same sentence that both of the samples were taken randomly and independently. Okay, it's very important that we're listing those conditions whenever we are constructing either confidence intervals or whether we are doing significance tests. Okay, so what we're going to start out here first of all in example 1 is our focus is going to be to describe the sampling distribution. And so you want to make sure that when you're describing the sampling distribution, as I referenced on this opening page here, anytime you're asked to describe a distribution, we want to be thinking CUS more along the lines of just the center, the shape, and the spread. Okay? So here's what we're dealing with in this particular example. It says a potato chip manufacturer buys potatoes from two different suppliers, Riderwood Farms and Camberley Incorporated. The weights of potatoes from Riderwood Farms are approximately normally distributed with a mean of 175 grams and a standard deviation of 25 grams. The weights of potatoes from Camberley are approximately normally distributed with a mean of 180 grams and a standard deviation of 30 grams. Now, when shipments arrive at the factory, inspectors randomly select a sample of 20 potatoes from each shipment and they weigh them. Now, look at the difference here, the order of our subtraction. We're going to let the difference in the mean weight of Camberley minus the sample mean weight of Riderwood Farms. That is the difference in sample mean weights of potatoes from the two suppliers. Our first question here is to describe the sampling distribution of the difference between the mean weight, sample weight in Camberley minus Riderwood. So let's take the information that I have highlighted up above and let's go ahead and write that down. Okay, in terms of Riderwood, I'm going to put a little R here so we know that's what this is talking about. We know the shape is normal. We know the mean is 175 grams, standard deviation 25 grams. For Camberley, the mean is 180, standard deviation 30. Now, it's asking us to describe the sampling distribution, and so this is where we're essentially thinking CUS, mostly focusing on these three elements right there. Okay, so for our center, okay, the center of the sampling distribution for the difference in these two sample means is simply subtracting the two sample means. Now, you'll notice, make sure you're doing this in the correct order. This is asking you to do Camberley minus Riderwood, so make sure you're doing this correctly. 180 minus 175. The difference, the average difference here is 5 grams. Okay, now for the spread. Okay, the spread. Before I actually use the formula, which is on the formula sheet, I need to make sure that I am satisfying the 10% condition. Okay, now there are two samples that are being taken here. It does mention that they are randomly selecting a sample of 20 potatoes from each shipment. So I don't need to show this calculation twice. I'm going to take 10 times 20, that equals 200, and then I'm just going to make a statement that that's less than or equal to all potatoes from, and I'm just going to say each company. Okay, so that'll satisfy for both Camberley and Riderwood Farms. Okay, I'm also just going to mention basically what that conclusion is then, since the 10% condition is satisfied, that means that our samples can be concluded that they are independent. Okay. Okay, so now I can use the formula. This is on the formula sheet. It looks like it's rather complex here. But it's essentially the square root of two fractions. The denominator of the fraction are the sample sizes of each of the two samples, which these were each 20. The numerator is the variance from each of them. It doesn't matter the order you put these in. The variance is the standard deviation squared. So you can see I'm taking this standard deviation, squaring it, and that standard deviation, squaring it. Okay, this comes out, if we type this into the calculator, to 8.73 grams. Okay, so now the last piece here is going to be describing the shape. Okay, there is a condition for me to be able to say that this is approximately normal. Okay, and we can see on the front I had what it is we would want to be able to, the reason we can say this is approximately normal. Okay, here's our three options. If we were told that both of the populations were normal, then we can conclude that when we combine them together like this, that the combined population or our combined samples would also be normal. Okay, now it did tell us that each one was normal. Riderwood Farms, approximately normal. Camberley, approximately normal. So I can just cite approximately normal because both populations were normal. Okay, and that allows me to then summarize that Camberley minus Riderwood, the shape is normal, the center would be 5 grams, and the spread 8.73 grams. This would be the information that I'm probably going to want to use to answer part 2 to this problem, which is to find the probability that the sample from Riderwood Farms would have a higher mean than the sample from Camberley. Now, let's be very careful about this. I'm going to go ahead and draw my curve. I know the average difference, and note that the difference, though, is Camberley minus Riderwood. The average difference is 5 grams, so I'm putting that down the center. Now, if Riderwood is higher than Camberley, then, and my order of subtraction, though, was Camberley minus Riderwood, this difference would need to be negative. Okay, the difference would be negative if Riderwood is a larger number than Camberley. So what I'm really after is I'm after anything where this difference would be negative. So I'm going to mark where roughly 0 would fall, and I'm going to shade everything to the left of 0. That represents where Riderwood would be greater than Camberley. Okay, so now I'm going to be doing normal, CDF. Okay, here are my inputs that we always need to make sure that we are labeling. Okay, my lower bound, I'm going all the way back in the left tail, so negative 10,000, 0. The mean, I'm just pulling right from each of these, and the standard deviation, and I get my answer to be, there's a 28.34% chance that Riderwood would have a larger mean than Camberley. Okay, we're going to try one more problem similar to that, and we'll move on to one other thing here in this video. Okay, so again, we are asked to describe the sampling distribution for the difference between two sample means. Let's look at what the context is here for this particular problem. It says a fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large drinks. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid L dispensed by the machine follows a normal distribution with a mean of 27 ounces and a standard deviation of 0.8 ounces. When the medium setting is chosen, the amount of liquid M dispensed follows also a normal distribution with a mean of 17 ounces and a standard deviation of 0.5 ounces. To test the manufacturer's claim, the restaurant manager measures the amount of liquid in each of 20 cups filled with the large setting and 25 cups filled with the medium setting, letting, look at the order of the subtraction here, the average of the large cup sample minus the average of the medium cup sample. That represents the difference in sample mean amounts of liquid under these two settings. We want to describe the sampling distribution. I'm going to take what I have highlighted and I'm going to write it in this abbreviated fashion here so I can see the shape, center, and spread for the large cups as well as the medium cups here. Okay, and then we're going to work through the center. There is no condition for the center. This is just representing the center of the sampling distribution for the difference in large minus medium cups here. 27 minus 17, that would be 10 ounces. Okay, as far as this spread goes here. Okay, now spread, we would normally think we would be doing the 10% condition here. 10% condition is where we take 10 times the sample size, make sure that's less than or equal to the population size here. Okay, so one of these we were sampling, 20 large cups, I believe, and the other one was 25 medium cups. We need to make sure that we're just saying these are less than or equal to all the large cups and all the medium cups. Okay, if we can check that off, we can conclude that this is independent, which then allows us to move forward and use our formula here for spread, standard deviation. Okay, again, formulas on the formula sheet. Denominator are the sample sizes, numerator are the variances for those. Okay, this is for the large cups. I'm grabbing standard deviation, squaring that. This is for the medium cups. Okay, this comes out to 0.20. Okay, so I'm just going to highlight this information so it's easy to pull here. The center is this, the spread is that, and now we need to talk about the shape. Okay, we want to be able to say that it is approximately normal, but we have to be able to give a reason. Okay, we have three options here. The easiest is if they told us that both of the populations were normal. They told us that right here, that the large cups and the medium cups were both normal, so I can say approximately normal because both populations were normal. Okay, so this is going to allow me then to go ahead and pull all of this information together. Large minus medium, 10.2. That would be the information I could use if this problem moved forward with asking a probability question. Okay. We're just going to take a look at confidence intervals for the differences between two sample means and walk through one example of this, and then we'll bring this video to a close. Okay, just to revisit this idea of confidence intervals, please keep in mind the acronym that I had shared with you before to keep straight confidence intervals for proportions versus confidence intervals for means. The acronym was ZAP-TAX. And the X in tax had a little bar over it to designate that any time we're dealing with means, we are using t-scores, we are not using z-scores. Z-scores are exclusive to proportions, and t-scores are used with means. Okay, so what you have right here is just the generic formula that you'll see on the formula sheet for confidence intervals. You take your statistic plus or minus your critical value times the standard deviation of the statistic. Okay, now that for a one sample t interval, if you're just trying to estimate a confidence interval for where a mean would be located from one population, is simply this formula here. Okay, we know that the degrees of freedom is always 1 minus the sample size. Well, if we're talking about drawing out two samples, one from each of two different populations, and calculating their difference, you'll notice this part of the formula is the same. However, what's different is now where the statistic is, that's the difference in the two sample means, still dealing with a t-score, and this is what I'm using as my standard deviation of my statistic. Okay, again, that formula is on the formula sheet. We will have to piece them together, like knowing that that gets plugged in there, this is our t-score, and our statistic is the difference. Now, when it comes to degrees of freedom, okay, degrees of freedom, we want to make sure that you are using for your degrees of freedom whichever is smaller, okay? So whichever sample size -1 is smaller, that's the degrees of freedom that you would use to help you find your t-score, your critical value. So for example, if one of your sample sizes was 50 and the other one was 45, you should use as your degrees of freedom 44. The smaller sample size -1, that is a more conservative way to find your t-score here. Okay, so let's see if we can walk through an example of how to find a confidence interval for where the difference of two sample proportions would be located here. Okay, here we're talking about the Wade Tract Preserve in Georgia. It's an old growth forest of longleaf pines that has survived in a relatively undisturbed state for hundreds of years. Now, one question of interest to foresters who study the area is how do the sizes of these longleaf pine trees in the northern and the southern halves of the forest compare to each other? So to find out, researchers took random samples of 30 trees from each half of the forest. 30 from the northern, 30 from the southern, and they measured the diameters of these trees at the breast height. So DBH is going to represent the diameter around the tree at breast height. Here are comparative box plots. You can see this top one here is for the northern, and the bottom one here is for the 30 trees in the sample from the southern. And there's some summary statistics down here showing you sample size, mean, and standard deviation. The question is, construct and interpret a 90% confidence interval, but look at what it says, for the differences in the mean diameter breast height of longleaf pines in the northern and southern halves of this Wade Tract Preserve. Okay, so I have some steps outlined here for us to help us through this first one. When we're doing these confidence intervals, we want to think through the process state, plan, do, conclude. So for the state portion, we always want to define the parameters. Okay, keep in mind these are the parameters. You should not be writing X bar. A parameter is a mu symbol talking about the population. This would be the true population mean DBH for diameter breast height for the northern trees. Okay, and then we're going to define what mu sub s is, which is essentially that same thing, but just for the southern trees. Okay, I know this is a lot of writing, but these graders need to make sure that you're being very clear what your variables are representing. In addition to defining mu sub n and mu sub s, you need to say, what is it that we're estimating? We are estimating where does the true difference in these two means lie? And we're going to do this at a 90% confidence level. That's what the problem up here was asking us to do. The order you're subtracting these in does not matter. Okay, I just chose to do northern minus southern. Okay, let's move down to the plan step here. In the plan step, you can see here it says we should be listing our conditions and we should name the inference procedure that we will be performing. Okay, now there are actually 4 conditions when we're talking about drawing from 2 different populations, but we can weave 2 of them in the first statement together. We want to say that both samples were taken randomly and independently. Okay, and I believe this problem mentioned that these samples there were random samples of size 30, and we're just going to assume that when they drew these samples one from the other, they were taken independently from each other. Okay, so we do need to make that statement there. Okay, number 2, we're going to do the 10% condition. Now, the sample sizes were 30 for each of these, so I only need to show this once. So I need to just make a statement that 300 is less than or equal to all trees in each half of the forest. Okay, and then my third condition is for normality. Now we know when we're doing proportions, we would do the large counts condition, which is the number of successes and the number of failures is at least 10. When we're doing means, we're looking for something different. We want to either do one of 3 things. Now I'm just going to scroll back closer to the front so that you can see what these are. We had this on our opening page actually, so I'm backing all the way back up to here. It did not tell us at all that both of the populations, the northern and the southern, were normal, so I can't use that as my reason for why I'm saying the shape of this sampling distribution is normal. I want to next then look and say, well, are my sample sizes both greater than or equal to 30? If that's true, then I can use the central limit theorem. If they're not greater than or equal to 30, then I could look at those box plots and looking for extreme skewness or outliers, I could comment that if there is no extreme skewness or outliers, that's approximately normal. Now, in this particular example, I know they gave us the box plots, but they did give us the sample size. The sample sizes for each of these was 30. It's right at that mark there. I could say this is approximately normal since both samples are greater than or equal to 30. And I'm just going to put CLT to abbreviate and show that I'm citing the central limit theorem for that. Okay, the other piece to this is I should name the inference procedure. You can see at the top of this notes page here, this procedure on the calculator is called a 2 sample, because we're taking 2 samples, T interval. T, because we use T-scores when we do means. Interval, we're talking about a confidence interval, not a significance test, a confidence interval. So we're going to call this a 2 sample T interval for difference in means. Okay, that's what we're trying to locate, the difference in means. When you're doing these problems, you really want to make sure that you're just always using the calculator. It's just a lot easier to use the calculator feature it gets really complex to use the formula. So you want to press that stat button. You want to bump over to the test menu. You want to select the option, I think it's 0 on my calculator, called 2samp t interval. Okay, and you're going to want to choose not data, but stats for the input. Okay, and you should always be recording what your calculator inputs are. So it's going to ask you for the sample mean and the sample standard deviation and the sample size for each of your two samples, okay? And this is just the information that's provided up above here. You can see they were each 30, and I'm basically just copying this down, telling the grader this is the information I put into the calculator. So this will be for the northern, oops, sorry, I put that sample size there. The mean for the northern was this, 30. Okay, this was also 30 over here. And then this is for the southern. Okay, these are just my calculator inputs. Also, something definitely worth noting, I always say no to the pulled option. Okay, we always say no to the pulled option for sure here. Okay. All right, let me get that information just plugged into my calculator here briefly, because we also, something else that we should be writing down is we definitely want to write down what the degrees of freedom are. Okay, the graders are going to want to look for that. We're doing a 90% confidence interval, no to the pulled option, and we're going to hit calculate. This is going to spit out my confidence interval. Okay, it looks like this is my confidence interval here. And I can see that it reported on the screen degrees of freedom. Now, it might feel like this degrees of freedom is different than what I had just mentioned about you take the smaller of the two sample sizes minus 1. You would use 29 for your degrees of freedom if you were doing it by hand using the formula. If you're using the calculator, just report whatever the degrees of freedom is from the calculator. In this case, 55.73. Now, you do have to draft a sentence to wrap this up. Okay, how we draft all of our confidence interval sentences, we say we are 90% confident that the interval, then we state the interval here, captures, now what are we capturing here? If you look all the way back up at the original problem, it will define for you right here, this is what we're looking to capture, the difference in the mean DBH of longleaf pines in the northern versus the southern trees, okay? So very important that you have this word difference, okay? Captures the difference between the true population mean DBH in northern minus southern trees. Okay, that brings this video to a close. You can see that there are about 3 examples here that you can go ahead and try that go along with these notes.